Hello, everyone, and welcome to Lecture 9. Obviously, we're going to start this the way we normally do. We're going to review a little bit from Lecture 8, and then we'll start talking about material from Lecture 9. Again, if you have any questions, comments, problems, please let me know. Obviously, I prefer to know the lecture number, the approximate time, and what your question is, and I will do my best to answer those questions. All right, let's see if we can do some review here, and then we'll get to our new material. So review. Awesome. Consider ClF3. What is the Lewis structure of this molecule? So we're going to have to draw a Lewis structure. What are the formal charges in chlorine and fluorine? We can do that from a Lewis structure. How many bonds? I'll be able to tell that from a Lewis structure. How many lone pairs on Cl, if any? I'll be able to tell that from a Lewis structure. What is the electron geometry of this material? We'll start there. What is the molecular geometry of this compound? We'll be able to get that from our happy table. And what are the approximate bond angles here? And again, that is something we should be able to look up from the table that we have as a reference, okay? So let's take a look. And the way that we're going to do this, we'll take a look at a piece of paper, happy blank paper here, and of course, I have a cheat sheet so I can look and see what those questions were again. We're talking about ClF3. Actually, ClF3. And I want to know Lewis structure, formal charge, chlorine and fluorine, number of bonds, number of non-bonding pairs, lone pairs, electron geometry, molecular geometry, and bond angles. Okay, so those are the things I'm looking for. So I have chlorine and fluorine, both of which are halogens. That means that chlorine, being a halogen, has 7 valence electrons that it can donate to this structure. Fluorine, being a halogen, has 7 valence electrons each, and there are 3 of them. It gives me a total of 21 electrons from the fluorine, plus the 7 from the chlorine. That gives me a total of 28 electrons that I need to be able to put into this structure. Now, to draw that, Cl is our center. A fluorine, a fluorine, and a fluorine. Does it matter where I put them? No, it really does not. For now, we're just trying to get the electrons dealt with. So we don't really care what those bond angles look like or anything else. Lewis structure doesn't care about that. All right. I know that I need at least one bond between each of these guys. So that gives me 2, 4, 6 electrons that have been taken up by the bond. So at least we have 22 electrons to put around these. I know that I need to fill the octet for the molecules on the exterior. Okay, so not my central atom, but everything else. So I want to fill the octets for all of the fluorines. So I'm going to do 2, 2, and 2. So each one of these fluorines is going to get 2, 4, 6 electrons, non-bonding electrons associated with it. Then with the bond, it has an octet. Okay, so I'm going to draw those on each of these. And yes, for Lewis structures, we need to show all of them. Okay, we can symbolize the bond as 2 electrons. We don't need to explicitly show that, but it is okay if you do. So that was 2, 4, 6 on each one. 6 times 3 is 18. So we'll subtract those out. That leaves me with 4 electrons left. Those 4 electrons have to go on my central atom to start with. So I'm going to put them there. And then my question becomes, do I want to move them? Is that going to be good for me to do? Well, if I were going to move one of those lone pairs into a bond with fluorine, that would violate the octet rule for fluorine. And we've already violated the octet rule for chlorine. It's the central atom, and we can actually do that. But we aren't going to do it for anything that's on the exterior. Okay, so this is the best structure that I can come up with everything that I know. Okay, fine. Let's calculate formal charge for fluorine. Now, all of the fluorines look exactly the same. So we only have to do this calculation once. How do we calculate formal charge again? Formal charge is equal to the valence electrons minus half of the bonding electrons minus the non-bonding electrons. Okay, so valence electrons for fluorine, we have 7 of them. We subtract half of the bonding electrons. So this fluorine has 1 bond containing 2 electrons. And then we're going to subtract the non-bonding, 2, 4, 6 for each of them. So 7 minus 1 minus 6, formal charge is 0. Chlorine, we have 7 valence electrons minus half of the bonding electrons, 2, 4, 6 in this case because there are 3 bonds, minus the lone pairs, the non-bonding electrons that are on chlorine, 2, 4. 4 electrons there. So 7 minus 3 minus 4, formal charge is 0. Okay, so 0, 0. I have 3 bonds. I have 2 non-bonding pairs on my chlorine, the central atom. My electron geometry is based on 5. I have 5 things around that I need to deal with. I can't do that without a table. So let's find a table. And we'll pull this table up and take a look at it. I can get it to where I want it. All right, and we'll zoom in just a little bit so that we can see this. Now, this says bonding and then lone. So we don't have anything where it's just bonding and then, the rest of it. This is arranged slightly differently than the one that I gave you before. So bonding pairs, I have 3. There are 2 non-bonding pairs. So I'm looking for the one that's 3 and 2. 3 and 1, 3 and 2. And notice it says an example of ClF3. Oh, awesome. That's good. Now it says that the electron geometry, or the geometry of the electron pairs, is trigonal bipyramidal. Okay, awesome. It also says that the molecular geometry, only the 3 that are there, is T-shaped. Notice that we have the fluorine here going through to the other fluorine on the other side, and then down to the fluorine that's here. So that is T-shaped because we're ignoring those non-bonding pairs that are up in here. Okay, so that's T-shaped. The last thing it asked me about was the bond angles. And it says from this table that the bond angles are approximately 90 degrees. Oh my Lord, I did it. So that's everything that you needed for that particular question. Hopefully that's clear. If it's not, please let me know and I'll be happy to answer any questions that you have. I'm just going to do this so that I have clean paper when I pull it back up. So obviously we come to the questions, comments, problems. All right. Now it occurred to me while I was making this particular lecture that what I do every single time is pull up from the lecture schedule. What are the sections of the textbook that we're going to be talking about in this particular lecture? Build my lecture and then delete this. I got tired of deleting it and I think it's stupid that I do that because it's almost like I'm hand waving and pretending that this wasn't there. I'm going to leave it here and I will try and go back and add it to the other ones as we move towards the final just so you can see them. But for this, we're going to be talking about 5.2, which talks about pressure of a gas, units of pressure, and atmospheric pressure. 5.3, the gas laws, Boyle's law, Charles and Guy Lussac's law, the Kelvin temperature scale, and Avogadro's law. And we'll talk about section 5.4, the ideal gas equation, gas constant, and the density calculations. We'll talk about 5.5, which is gas stoichiometry, and 5.6, which is Dalton's law of partial pressures. We'll then move into chapter 11, section 2, which is intermolecular forces. We will specifically talk about dipole-dipole interactions, ion-dipole interactions, dispersion forces, van der Waals forces, and hydrogen bonding. Okay, so questions, comments, problems about that? Well, then let's get into it. First, we're going to talk about the pressure of a gas. Definition and units of pressure. Pressure is defined as force per area. So it's a way for us to talk about how much those gas molecules hit whatever they're getting in, whatever's around them. So 1 Pascal, which is our units that we're going to talk about, is 1 Newton per meter squared. If you're interested in how we got those units, section 5.2 has the details on why those are the units that we have. I don't think it adds anything to our discussion to tell you that that's what a Pascal is. It's also not typically the unit that we use for this, but it is related to all of the other pressure units. Okay. Now, pressure is, again, defined as a measure of how often a gas molecule hits the wall of the container that it's in. That is a function of how big that container is and how much gas is inside that container. Okay. Units that are used to measure pressure include millimeters of mercury, mmHg, torr, Pascal, kilopascal, and ATM. So ATM is atmosphere. Manometer is used to measure the pressure of a gas other than the atmosphere. Okay. There are descriptions of a manometer and how it is used to get the pressure of gas, over water in your textbook. Atmospheric pressure is the pressure exerted by the Earth's atmosphere. So all this gas that's in the atmosphere is the pressure that's exerted by that. That's going to vary based on a couple of things: location, temperature, and weather conditions. You should see why that is as we go through this conversation. Standard atmospheric pressure is 1 atm by a barometer. 1 atm. Now, how do we define 1 atm? It's the pressure that supports a column of mercury to exactly 760 millimeters high at 0 degrees C at sea level. Okay. Now, it varies a little bit depending on where you are. Am I at sea level? Is the temperature 0 degrees? But we use that as a conversion factor. 1 atm is 760 millimeters mercury. Okay. But that's how that's defined, and that's what we talk about for that. Questions, comments, problems on that? Then let's talk about gas laws. So in order to talk about gas laws, we're going to need to define some variables first. P is pressure, V is volume, T is temperature, R is the gas constant, and N is the number of moles. All right, how are these things related? Well, Boyle's law says that pressure times the volume is a constant. Pressure and volume are inversely proportional. As I increase one, the other one has to go down. So if I increase the pressure, that's because the amount of volume that I have is smaller. Same amount of gas, higher pressure means smaller container, and I'm hitting those walls more often. Converse, if the pressure goes down, that means for the same amount of gas that I have more room to move and I hit those walls less. Okay, so P1 V1 equals P2 V2. So I have a set of initial conditions given by an initial pressure P1, initial volume V1, and then I can change them and say, okay, now I'm going to change the pressure to twice what it was. What happens to the volume? I'm going to change the volume to half what it was. What happens to the pressure? That kind of thing. So if we're changing conditions for pressure and volume, that's why we use P1 V1 equals P2 V2. Okay. Charles' law, and also Gay-Lussac's law, we always call it Charles' law, but they were both involved in this, gives us V1 over T1 equals V2 over T2, and P1 over T1 equals P2 over T2. What that means is that the volume and the temperature are directly proportional, and the pressure and the temperature are directly proportional. Okay. Again, we can talk about V1, T1 as initial conditions, V2, T2 as changed conditions. Same for P1, T1, P2, T2. Okay. So there's our relationships there. We'll get to how all of this fits together in just a second. Avogadro's law deals with number of moles. So the number of moles is proportional to the volume. All right. We'll talk about exactly how that's true in a minute. So if we have a container that can expand, and we put 1 mole of gas in it, it has a fixed volume. If I then add another mole of gas, it's going to have twice that volume. Okay. So that's what we're talking about for that. So the number of moles determines the volume if we can expand to whatever volume we want. So we need to know that there is a relationship for volume and number of moles of gas. Temperature here is on the Kelvin scale. So when we talk about temperature, it's Kelvin. degrees C plus 273.15 is how we get from degrees C to Kelvin. You can get from F to degrees C using that big, huge, ugly equation that has fractions in it. That you should have it on the test if you need it, okay? But we do need that to be in Kelvin. Awesome. We can do that. All of those are wonderful definitions. Definitions, equations, calculations. And we'll get to the calculations in just a little bit. But first, let's talk about the ideal gas law. So the ideal gas law is that the pressure times the volume equals the number of moles of gas times the gas constant times the temperature. PV equals nRT. Pervner is one of the ways that we mnemonically talk about this. Okay, Pervner. Awesome. Now, R is the gas constant. We typically use this as 0.082057 liters times atmospheres, whole thing divided by moles times Kelvin. We often round this to 0.0821, and you'll see me do that all the time, but that is the full definition right there. Awesome. Great. We'll talk about that a little more in a second. Now, the molar volume of a gas. So if I have 1 mole of gas and it can occupy as much space as it wants at 0 degrees and 1 atmosphere, which is defined as standard temperature and pressure, 0 degrees, 1 atmosphere. That 1 mole of gas will occupy 22.41 liters. So we'll see this conversion factor, that 1 mole is 22.41 liters, okay? And again, that's going to vary slightly as we talk about different temperatures and pressures. It's usually not enough for us to want to talk about it being different. For our purposes, that's close enough. For changing conditions, if the number of moles of gas is constant, we see the following relationships. P1 times V1 over T1 equals P2 times V2 over T2. Now, all this is a combination of the equations that we talked about on the last slide. P1, V1 equals P2, V2, V1 over T1 equals V2 over T2, P1 over T1 equals P2 over T2. It's just a combination of those things. Why am I telling you this? Because if we're changing conditions, this is what we want to use. Now, having said that, if the pressure remains constant, then we only need to worry about V and T. If the volume remains constant, then we only need to worry about P and T. So those constants will drop out. So this will give you whatever relationship you need if you know what's constant. Okay, so this is the one you want to remember, and you want to know how to use it. And again, that's if N is constant. All right. We typically don't talk about changing N, but that's beside the point. We can do a couple of other weird calculations using the gas law. So density calculations. Remember, density is the mass per volume, M over V, mass per volume. And that's equal to the pressure times the molar mass divided by the gas constant times temperature. Now, how did I get there? Well, I know that there is a way that I can talk about PV equals nRT. N is related to the number of moles. The number of moles can be manipulated using the molecular weight. Then I could divide that by the volume, So that's how we get there. And if you want to go through that exercise, I'm happy to show it to you, but I'm not going to do that for the general folk. It is just substitution and rearrangement. So density is equal to P times M over R times T. We can also find the molar mass, and that's equal to the density times R times T divided by P, where D is the density of the gas. Okay, so if I want a molecular weight, and I know the density, the gas constant, temperature, and the pressure, then I can calculate the molar mass. Please note that there are a lot of other units for R. I've given you one. But this is the one that we use most often in chemistry. Well, why? It was defined as pascals before. We typically don't work in those units. What we typically work in are units that are more common to us. Volume in liters, pressure in atmospheres, N being the number of moles. So unit is mole. And temperature in Kelvin. So that's why those units are there, and that's why that's the gas constant that we use most often, because we need to be able to convert using those particular units. Now, this should imply a couple of things to you. One, we need to make sure our units are right, i.e. those units, liters, atmospheres, moles, Kelvin, before we do any calculations. So we're going to have to do some pre-conversions before we get into what we're looking for. And then we have some calculating and moving things around that we may have to do. All right? So let's see if there are any questions. If there are, you know how to contact me. If there are not, let's see how this moves to calculations. But first, I need to remind you of the stoichiometry mole island diagram. And when in doubt, convert to moles. I don't care what you're doing, you have to convert to moles for most of this, and you need to have a balanced equation to be able to go from moles of one thing to moles of another thing. All right? When I say when in doubt, convert to moles, I usually say that because if you convert it to moles, while you're doing that conversion, it tends to give your brain a little space to think about what else you might need to do, how you can put the pieces you have together. So when in doubt, convert to moles can get you started. And if nothing else, you've done at least one calculation that you needed to do. All right. So I said before, when I presented this the first time, that we were going to ignore the volume, which is related to gases. This part right here is now coming into play. So we know that we can go from the volume of a gas. 1 mole is 22.4 liters. We can use that to get from volume to moles, from moles of A to moles of B, and then from the moles of B to the volume, to the mass, to the particles. And the same is true over here. We can go from mass to moles, or particles to moles, and then from moles to moles, and all through this, okay? All of those are related, all of them are connected, and we can do any of those conversions that we need to do to be able to go from what we know to what we want, all right? And it's just a question of knowing which conversion factors you need to be able to do that. So let's see how this plays. Example calculation. Now, I've written the ideal gas equation again, PV equals nRT. Let us consider 2S solid plus 3O2 gas plus 2H2O liquid goes to 2H2O H2SO4 aqueous. What is the volume of O2 in liters at 22 degrees C and 745 millimeters of mercury pressure is required to produce 1.00 ton of H2SO4? Oh my God, that's a lot of information. And I know a lot of people look at this and go, what am I supposed to do with that? Well, let's take a step back and let's start writing stuff down. So the first thing that was written down for us, PV equals nRT, because I might need that. I am considering the equation 2S solid plus 3O2 gas plus 2H2O liquid going to 2H2SO4 aqueous. All right, so this gives me my molar ratios. I can check this and see that it's actually balanced. 2 sulfurs. I have 4 hydrogens, 6, 7, 8 oxygens there, 8 oxygens there. So it's balanced. Awesome. Should you do that? Absolutely. Just because it's been given to you doesn't mean it's right. All right, so make sure that you have what you need. I have been given a temperature, 22 degrees C, and I've been given a pressure, 745 millimeters of mercury. Now, if I don't know what those are, should I write them down? Absolutely you should, because you should look at them and go, okay, what variable does that go with? All right, that's something that we're going to need to talk about. Now, the other thing that I want to know, I want to make 1.00 tons of H2SO4, and I want to know what is the volume of O2 that's required to do that. Now, why did I write this stuff where I wrote it? Notice that I put how much H2SO4 I want above H2SO4. That reminds me that I'm looking for that amount of H2SO4 when I'm doing this. I've also put this question V over 302 because that's what is the volume of that's required to do this. All right, that's awesome. Now, one other thing I'm going to write down. R equals 0.0821 liters times atmospheres over mole times Kelvin. Why did I do that? Well, I'm going to need it. If I'm going to use PV equals nRT, I'm going to need it. The other thing is it shows me the units that I need to be able to do this. And immediately I see a problem. So this is not in Kelvin, so we're going to need to convert that to Kelvin. This is not in atmospheres, because we're going to need to convert that to atmospheres. And this is not in moles. So I'm going to need to convert that to N. Let's start with the easier things. So I'm going to start with the easiest. So let's convert our temperature. So 22 degrees C plus 273.15 equals 295.15 Kelvin. Okay. Now let's talk about our pressure. That's 745 millimeters of mercury. I know that 1 atmosphere is 760 millimeters of mercury. And that gives me an answer of 0.9802631579 ATM. Now notice, I have not truncated anything at this point. I have all of the digits that are there because I need to carry all of those through when I do my calculation and wait until the very end to round, truncate on those. All right. So now I have a pressure, now I have a temperature. Both of those are in the units that I want. Pressure, temperature. I don't know the volume. So let me remind you that we're looking for volume. So the volume is going to be equal to number of moles times the gas constant times the temperature divided by the pressure. Okay, so I have T, I have P, I have R, but I don't have N. I need to know the number of moles. So I know that I want 1.00 ton of H2SO4. And I need to do something with that. Well, I also know from the conversion that I looked up, which you'll either be given or you will be somewhere that you can use it. I know that 907,185 grams per ton. And so that'll give me the number of grams that I have. 9249. Oops. 907185 grams of H2SO4. 907185 grams of H2SO4 is not in moles, so I'm going to convert that. When in doubt, convert to moles. The molecular weight of H2SO4 is 98.079 grams per mole from my periodic table. And that gives me an answer of 9249.533333539 mole H2SO4. Whew. So my volume is going to be equal to nRT divided by P. Okay, nRT. So this is N, 9249.533333539 mole times R, 0.821 liters times atmospheres, mole Kelvin. Temperature is, where did I write it down? 295.15 Kelvin. Kelvin cancels with Kelvin, mole cancels with mole. I want liters, so I need to have that atmospheres in there. And that was 0.980263 ATM. Good God. That's a lot of stuff. All right. So let's pull this up. We'll clear this out. And I have 9249.5333539 times 0.0821 times 295.15 divided by 0. Sorry. I keep forgetting I can't go back on this. 0.980263 atmospheres. And that was not right. Sorry. I screwed this up. This should be point. There we go. Enter. 228,645.762. Yay. Now, that's the number that I come out with. So I don't like this number for two reasons. One, it's a big number. I don't really like that. So I'm going to put it in scientific notation. That's one. And two, it needs to be 3 significant digits. So if I put this into scientific notation and get the 3 sig figs, it's 2.29, because I round up, times 10 to the 5th liters of H2SO4. Okay? Yahoo! And of course, I can click the mode. I can click the science. I can click enter. I can quit that. And then I can multiply my answer times 1. And that gives me 2.28 and changed times 10 to the 5th. So that's how I know what that is, because I can't do that in my head. I'm not very good at it. Okay? So that's how we get to our answer. Questions, comments, problems on that. Let me find this. Questions, comments, problems. Sweetness. So we calculated that. Let's talk about Dalton's law of partial pressures. So partial pressure ideal gas law. This is a derivation of the ideal gas law that's meant for partial pressures. So the pressure that is measured in the atmosphere comes from a mixture of gases, N2, O2, He, Ne, and CO2 being the primary components. The contribution from each gas can be calculated using a modification of the ideal gas law. So the pressure from that one gas is equal to the number of moles of that gas times R times T divided by V. The pressure from substance A is a result of the number of moles of A. Awesome. Total pressure from partial pressure. The total pressure is the sum of the partial pressures. So PT is equal to PA plus PB. It's always the sum of the partial pressures. Because the pressure of one gas can be written as the pressure of A divided by the pressure of T, that's equal to the number of moles of A divided by the total number of moles of A plus the number of moles of B. The pressure is a part of the total, so it can form a fraction. So PA over PT is a fraction. That fraction can be used to write what we call a mole fraction. So that number of moles of A divided by the number of total moles is equal to something called chi. Chi is a mole fraction. So we've gone from A to I, but chi I is equal to the number of moles of I divided by the total number of moles. This relationship leads to the following expression. The pressure of I times the mole fraction of I times the total pressure. Okay? So that's how we can do this. If I know the total pressure and I know the mole fraction, I can find the partial pressure. If I know the partial pressure and the total pressure, I can find the mole fraction. If I know the partial pressure and the partial temp and the total pressure, then I can find the mole fraction. Okay? So that's how all of those wonderful things are related. Yippee skippy. Let's see that in work. So these problems are actually from your textbook. You'll see it says 5.66, 5.74. Those are the ones that are in that end material for chapter 5. So that's the questions that you're looking at here. Awesome sauce. So let's work with our piece of paper and this first question. And I'm going to resize my paper a little bit so that we can see this first question. So for 5.66, a sample of air contains only nitrogen and oxygen gases with a partial pressure of 0.8 atmospheres and 0.2 atmospheres. So the pressure from N2 equals 0.80 atm. The pressure from O2, 0.20 atm. Okay. Calculate the total pressure and the mole fraction for N2, mole fraction for H2. So the total pressure is going to be the sum of the partial pressures. So the 0.80 atm plus the 0.20 atm. And that's equal to 1.00 atm. Now, since I'm adding these, we go to the last decimal place. 2 decimal places on this one, 2 decimal places on this one, gives me a total of 1.00 atmospheres. Awesome. I also know that the mole fraction for N2 is the partial pressure of N2, so the 0.80 atm, over the total pressure, which is the PN2 for PT, which is 0.80. No units on that as it's a fraction. Mole fraction of O2, it should be O2, is then 0.20 atm over the 1.00 atm, which is 0.20. Go me! I did it! I found the total pressure, I found the mole fraction of N, and the mole fraction of O2. Now, if I wanted to, I could go through the whole calculation of what is the number of moles of N, what is the number of moles of O2. I can do all of that, but it comes out exactly the same way, all right? So that's 5.66. Awesome sauce. Let's move over. Now let's talk about 5.74. 5.74. Sample of ammonia is completely decomposed to nitrogen and hydrogen gases over heated iron wool if the total pressure is 866 millimeters of mercury. Calculate the partial pressures of N2 and H2. Well, the first thing I have to do, I know that NH3 goes to N2 plus H2. I'm going to balance the N2. I need 2 NH3s. 2 NH3s gives me 6 hydrogens. So I need that there. So that's my balanced equation for this. And I know that the total pressure, 866 millimeters of Hg. Awesome. Calculate the partial pressure of N2 and H2. All right, so I want to know the pressure from H2 and the pressure from N2. Well, I know that the pressure of H2 is the mole fraction of H2 times the total pressure. And the mole fraction of the pressure of N2 is the mole fraction of N2 times PT. I can rearrange this, and I can get the mole fraction of H2 is equal to P of H2 over PT. And I can do that. Actually, never mind. Mole of N2 over total moles. From my balanced equation, I know that there's 1 mole of N2 for 4 mole total. And I know it's 4 moles total because there's 1 mole of N2 and 3 moles of H2. So it's 4 moles total. Okay. All right. That means that I'm going to have my mole fraction 1/4 times the total pressure, PT. So 1/4 of 866 millimeters of mercury. And that gives me 217 millimeters of mercury. Awesome sauce. Now, do I need to change my units? Nope, didn't tell me to, so why should I? X of H2 is equal to 3/4 of PT. And again, it's 3/4 because there's 3 moles of H2 and a total of 4 moles on that. So that gives me 3/4 of 866 millimeters of mercury. And that's equal to 650. I also know that 866 millimeters of mercury minus 217 millimeters of mercury should give me the 650. And if I do 86, where's my calculator? 866, 866 minus 217 gives me 649. Close enough. All right, it's a rounding issue that we come up with there, but that's what we're looking at. Now, can I go through the whole pressure grids? Yes, absolutely I could, but this is going to give me the answer that I'm looking for. Questions, comments, problems on that one? Hopefully not. Now, let's get us a clean piece of paper. Let's drag this over here. And then let's go to our next slide. And then put our paper back up. No, I don't want my calculator yet. I want my paper. Oops. So 5.104, and I apologize for the beeping that you hear, but we'll be done in a couple of minutes, so we'll take care of it then. 5.104, a healthy adult exhales 5.0 times 10 to the 2 milliliters of aqueous mixture with each breath. Calculate the number of molecules present in that particular volume. So that is a volume at 37 degrees C and 1.1 atm. That's the major components of this gaseous mixture. So first, we're going to convert our temperature to Kelvin, because that's what it tells me to do. So 37 degrees C plus 273.15 is going to give me what? 310. If I cut off the 0.15, 310 Kelvin. All right, the volume equals 5.0 times 10 to the 2 milliliters. I know that there's 1,000 milliliters per liter, and that gives me 0.5 liters. I know my pressure is 1.1 atm, and R, again, is 0.0821 liters times atmospheres per mole times Kelvin. And if I want number of molecules, that means I need to get to the number of moles. So N is equal to PV equals nRT. So N is equal to PV divided by RT. So 1.1 atm times my pressure, 0.5 liters, divided by temperature, 310 Kelvin, and 0.0821 liters times atmospheres, mole, Kelvin. Kelvin, Kelvin, atmosphere, atmosphere, liter, liter. So that gives me an answer with a unit of mole, which is what I want. And if I do all of that happy math, That gives me 0.022 mole of this gas. Okay. Now, do I know exactly what that is? No, but I'm not really concerned about it at this point. I multiply that by 6.022 times 10 to the 23rd particles. And that should give me the number of particles that I have. 1.3 times 10 to the 22 particles. Do I know exactly what it is? Not necessarily, but I'm guessing there's going to be CO2 in it. I'm guessing there's going to be H2O in it. I also know there's going to be some oxygen and some nitrogen. So those are the major components, right? Questions, comments, problems on that? Nope. Awesome. Let's keep going. Intermolecular forces. So I said we'd talk about intermolecular forces. I'm going to do this from weakest to strongest being on the next slide. Van der Waals forces are the weakest attractive forces between molecules. It exists in all molecules, regardless of shape or structure. I don't care what it is. There are some ways that those particular molecules are going to be attracted to each other. Now, dispersion forces form when electrons on nearby molecules create temporary dipoles that are attracted to each other. So in one molecule, I get a temporary condition where I have a negative one on one end, the next molecule has a positive on the other end, and those are attracted to each other. Those are my dispersion forces. Dipole-dipole interactions are attractions between molecules that have permanent dipole moments. So we can talk about water. That has permanent dipole. So we have one end that's negative, that's the oxygen, one end that's positive, that's hydrogen. That one water molecule at the negative end can be attracted to the positive end of another water molecule. That's a dipole-dipole interaction. Ion-dipole interactions are when an ionic charged particle is attracted to the dipole of another molecule. So if I have an ion, say sodium, and that's dissolved in water, then I can have the Na plus attracted to the oxygen end of that water. So the plus is attracted to the negative portion. That's an ion-dipole interaction. That's why water is such a good solvent for ionic compounds, and generally speaking, why most ionic compounds will dissolve in water. Not all of them will, and that's because their interactions, say for CaOH2, which is a non-soluble substance, those attractions in that molecule are stronger than the ion dipole would be if it dissolves in water. Okay? And finally, we're going to talk about hydrogen bonds. A couple of things about hydrogen bonds that we need to talk about. Hydrogen bonds are formed when hydrogen is bound to a highly electronegative atom, like nitrogen, oxygen, or fluorine. Those are the three that we'll talk about. And they can be attracted to another molecule of the same type. The affinity of the hydrogen on one molecule is strongly attracted to the nitrogen, oxygen, or fluorine on another molecule. All right, that's the strongest intermolecular force. It can create hydrogen bonds across many molecules. And those interactions create a much stronger interaction than what we would see regularly. Leads to higher temperatures for physical changes than we would have expected otherwise. What the hell? Well, let's look at water. The oxygen on one end can be attracted to the hydrogen on another one, the next one over. Those interactions are so strong over distance, so many of them, that we have a much greater boiling point for water than we would have thought would be the case, right? So that's what we're talking about for that. Questions, comments, problems with that? If you do, let me know. You know how to do it. Anything else? No. That brings us to the end of the material that we were going to talk about in Lecture 9. So again, that was Chapter 5 and Chapter 11. Questions, comments, problems on any of it, please let me know. but that takes us to the end of what we're going to share for that. All right, I'm going to go ahead and stop the recording on this, and I will stop the sharing first, and then I will stop the recording, and I'll see you guys soon.